This lecture carries on with our mathematical preliminaries that we started in the last lecture. This lecture we're going to spend most of our time on vectors. The last lecture was mostly about matrices, and this time will be mostly about vectors. And I think most of you, anyone who comes upon this lecture, probably has some experience with vectors already. And so we're going to kind of build them from scratch, but kind of rely a little bit on things you might have seen before. Sort of set a common ground for everyone watching these lectures and kind of talk about what are the things we expect of vectors. We'll talk about their geometric interpretation, particularly how you can think of them in 2 and 3 dimensions and how that's useful for building up intuition for thinking about them in higher dimensional scenarios, which are the most common ones that we'll encounter, to be honest, higher dimensional scenarios. And then we're going to talk about special types of vectors. So we'll talk about eigenvectors and what do those mean? What's kind of the general principles behind those? And then we'll talk about how are eigenvectors used in the description of diagonalizable matrices and what are those useful for? All right, let's get started. Okay, so we're going to start today by talking about vectors. In the last lecture, we introduced matrices. So vectors. For our purposes, it's possible to just think of vectors as matrices that have dimensions either n rows and 1 column or 1 row and n columns. So for us, we'll say vectors are n by 1 or 1 by n matrices. That's a pretty crude definition. Mathematicians might object, or they probably would. There's more sophisticated ways to define vectors in such a way that much more exotic objects than you might have thought of before can be considered vectors. But this will work for us. And so we're going to denote them, or they're often denoted with different notation. Sometimes people don't put any special notation on them at all, but we will use some notation to indicate a vector. So let's say you have a vector A. The notation I'll use will be an A with a little arrow over the top of it, like that. Another notation that I'll use is A with a little hat over it, but that'll be a special type of vector that we'll introduce today called a unit vector if it has a little wedge-shaped hat over it. So that one on the left is a regular vector, and the one on the right there is a unit vector. People also use other things. You might see, for example, or you might know from previous experience, some people put like a little tilde underneath. This is not a notation that I'll use. Some people just underline it. That's meant to be a straight underline. And some people put a little straight bar on top like that. There's lots of different notations. But these are the notations here that we will use. So those are the notations for vectors that we will use. And so let's just write out an example. So an n by 1 column vector. Right, and so that looks like this. So it's the vector A. Sometimes you'll say, okay, it's the grouping of the elements A sub I1, right? Because there's I different, I indicates the row, and there's only 1 column. But usually you don't put an index for the 1 because it's sort of redundant for a vector. And so you might say like this, the collection of AIs, A sub I's. And so for a column vector, they look kind of like this. So A1, A2, and then a bunch of space, other ones, and then down to AN, like that. And so that's a column vector with the numbers, the elements of A kind of lined up in a column like that. So similarly, for a 1 by n row vector, which we could build by taking the transpose of A here. So I'll do that. So I'll say this is A with an arrow over it, transposed. And so this is the collection of the elements, the transpose of A, row 1, column I, like that. And again, people don't usually keep track of that. They'll just say this is AI. And if you line them up, so it looks like this, A1, A2, and then over to AN, like that. So that's called a row vector because the elements are lined up in a row. For us, and in most contexts that you would encounter them, the default for a symbol with an arrow over it is a column vector. So if unspecified, the default is a column vector. And I think that's usually what people do. I don't know if I've ever seen anyone do the opposite. Right, so if you just see a symbol with an arrow over it, it means a column vector. So if we just wrote down an arbitrary V like that, it means that it looks like this, V1, V2, Vn, if you didn't specify it. And it means that the transpose of it is a row vector. Like that. So with this definition, we can carry over the rules for addition and multiplication from matrices. So addition and multiplication, either by other matrices or vectors or by scalars, use matrix rules. Because as far as we're concerned, these are matrices. And so, for example, what that means is that addition looks like this. Right, so addition says that if you take two vectors A and B and add them together, and you ask what is element I, that's element I of A plus element I of B. Right? So that's addition for us. And notice when you look at this that it has to be the case that both A and B have the same dimensions. Oops. A and B must have same dimensions. Sometimes people consider being possible to add vectors without the same dimensions, but what they really mean by that is they're giving 0 to one of the extra dimensions of the one that has fewer. But we'll just say they have to have the same dimensions. And so multiplication there's different ways to define multiplication for vectors, different common ways. And we're really only going to use one. And so we're going to say the following. So we're going to say, if you put two vectors next to each other like this, A transpose times vector B, then that just obeys matrix multiplication. So this is what I was saying. We can just use the matrix rules. And so if that's true, so A transpose is a row. And so what you want to picture in your head here is like A is lined up like this, and B is lined up like this. And so to get this multiplication right, you sort of tip B over and merge it with A, and it looks like this. So you get A1 times B1 plus A2 times B2, and so on, up to AN times BN. And that's how multiplication will work. This is a particular, so this is just an example of matrix multiplication. Of course, But usually people define this with just plain old vectors and not talking about their transposes necessarily. And this gets a name. This is called a dot product. So this is called, it's named the dot product. That's one name for it. It's also called other things like inner product or symmetric product, has other names, but we'll call it dot product. And you can write it like this. So A transpose times B is by definition A and then with a dot, like the same dot you use for ordinary multiplication, times B, A dot B. And that's how you read it. You say A dot B. And it's symmetric in the sense that it's equal to B dot A. And you can see if you look at this definition above here and put them in the opposite order, so B transpose times A, you would get the same thing. Like that. But the ordering there has to, of course, be correct. The one that's transposed has to be on the left, because that's the one that's converted to a row vector. Now, with matrices and scalars, we had some notion of size where you put vertical bars on either side of the thing. And so we'll have the same thing for vectors, but it's a different definition. So size, which I'll put in quotes. Usually people don't call it size, they call it magnitude or length. And that's a definition, that's a usage, that's a word that has meaning that makes sense, that we'll introduce for reasons that we'll discuss in a second. But the size or the magnitude of A looks like this. So you put vertical bars around it, just like you do for other things. And it's equal to a big thing under a square root. So it's A1 squared plus A2 squared plus dot 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 up to an squared. And all of that is under a square root, so to the power of 1/2. Right, so you can rewrite that as the vector A dotted with itself under a square root, or you can write that as, this is the common notation, and I will use this pretty heavily, just the symbol A. So if you strip away the arrow or a hat, or the arrow, no, not the hat. If you strip away the arrow from a vector, what you're left with is its magnitude. So this is a common notation where the magnitude of a vector is just represented by the same symbol without any decorations on it. Okay, so let's talk a little bit about the interpretation of vectors, which will help to make sense of why is this called a length. And again, this should be, for many of you, this is review. Even for those of you for which it's review, we should get to some things that you might have forgotten today. For those of you for which it's new, you really should consult a book to practice and get these things kind of stuck in your memory. And I recommend that third book on the list of books that I put on our Moodle webpage. That's a good place to start, maybe. Okay, so what I want to talk about is the interpretation. And this is a sort of a geometric interpretation. So what we think of is if you have a vector v, right? So for a vector v, its components, or the vi's, these are coordinates, or Cartesian. These are coordinates, Cartesian coordinates. Let's just say coordinates. For the head, or the arrow point of an arrow going from the origin of a Cartesian space. So it's probably better to say Cartesian coordinates. There's either the Cartesian coordinates for the head of an arrow that had its start at the origin. And so let's just draw a picture, right? So let's say you have a two-dimensional case, and these are your x and y axes, right? And suppose you have a vector v, and it has component. Let's just write it over here. So we'll say you have this vector v, and it's got two different pieces, v1 and v2, right? Then the way it looks is, I'll just draw it in the first quadrant here to make my life easier. So it looks like that, and this point here is at the location v1, v2. So in other words, x is equal to v1 and y is equal to v2 for the location of the tip of that arrow, right? And so this whole thing here is v, that arrow, and this piece here, the amount of distance that you had to travel over in the x direction to get to that point, that's v1, and the amount of distance that you had to travel to get to that point in the y direction, that's v2, right? So that's the sort of geometric picture here. And then of course it should make sense that the idea that the length squared, say, should be equal to v squared, and that's v1 squared plus v2 squared, which you can just see as the Pythagorean theorem in 2 dimensions. The Pythagorean theorem works in higher dimensions too, so if it was 3 dimensions, it'd be v1 squared plus v2 squared plus v3 squared. That would give you the squared length of the vector v, and so on, up to higher dimensions. Okay, so now I want to introduce some important concepts that I'm really just going to claim. So note. Now I just want to emphasize these are claims here. I'm not proving this. You should be able to prove these things. This one in particular, I should say. But you won't always be able to prove things that I'm just claiming in here. And we will do that a fair amount. So if we were doing like a proper linear algebra course, you would spend time proving all these things so that you could be, firm believers in them. But we're thinking of you as someone who either already has done that, and this is a review for you, or someone who hasn't done that but doesn't really have a lot of interest in making those proofs. And so this is just a claim, and the claim is the following. So let's say you draw the two vectors a and b, and they can be in a higher dimensional space if you want. So let's say this is the vector a, and let's say this is the vector b. Like that, right? Then if you make an angle between the two, like that, and we'll name it theta. And so here theta is the smallest angle between a and b, right? So for example, in 2 dimensions, the alternative angle is the one that goes around like that, right? So that's not what I'm talking about for the angle theta. It's the smallest angle. So this is the smallest between a and b. Smallest angle between a and the vectors a and b. Then it is the case that the dot product a dot b, or a transpose times b, let me just write it out. And again, that's just equal to a vector transpose times b, matrix transpose, a transpose times b. That is equal to the magnitude of a times the magnitude of b times the cosine of the angle between them. And that's a really useful concept because it helps you to picture a lot of things. So for a lot of things, we're going to be dealing with much higher dimensions than 2 or 3, but it's useful to kind of have this picture of the 2 and 3 dimensional cases so that you can kind of make sense of it. So think about this picture and that equation there, which again, I'm just claiming. I'm going to copy this. I'm going to duplicate it, move it down here, and I'm going to erase some of these bits. just the arrow there, really. Yeah, I'm going to move theta to the inside here because I need room. And then I'm going to copy this again. Well, I'll leave it for now. And so think about how this looks. If you look at this expression here, a times b cosine theta. A times cosine theta, if you make a right triangle like this distance here is a times cosine theta, where a is the magnitude of the vector a. Right, so that's a times cosine theta, that length there. And so therefore, the formula a times b times cosine theta, so a dot b, you can express it in the following way. You can say this is equal to, so what I want to look at is, here's a, and there's cosine theta, and the rest is b. And so this is b times the part of a that points in the direction of b. That's called the projection of a onto b. Right? Because this length here, if you were to like cast a light from above, say, this is the shadow that would be cast down onto the length, onto the vector b. So it's the part of a that points in the direction b, in the direction of b. Similarly, you could make that same picture. So I'm going to copy this again. Move it down here. I'm going to need a little more space this time. And do some more erasing. Erase all those little dots. I want to think of this same expression, but look at b times cosine theta, and think of it as multiplying a. And b times cosine theta, if you extend this vector like that, and make a right triangle, then this length here, we'll use orange again. This is b times cosine theta. Right? What I mean is it's this length here. Right? So it's the part of b that points in the direction of a. Right? So we say this is, you could have instead said this, and this of course has to be true by symmetry. This is a times the projection of b onto a. Now this is useful because we're going to do a lot of multiplying of vector transpose by another, or in other words, a lot of dot products, and this kind of geometric picture is handy. So notice in particular what would happen if a and a dot b were 0. So I'll put that off to the side here. Note a dot b, if a dot b is 0. Now you should pause the video at this point and think about it. What is the meaning of a dot b being 0, the sort of geometric picture? Well, it means, first of all, either it could be the case that the vector a has no length, which is kind of a pointless vector. No pun intended. It means that then you could get 0. But the alternative is it just means that the projection of a onto b is 0, or the projection of b onto a is 0, or in other words, the two vectors a and b are perpendicular to each other. Right, so that's what that symbol means. I should put this as implies. Right? So if a and b are actually perpendicular to each other, then the projection of one onto the other is 0. And so you would get 0 for that dot product. Or in other words, the angle between them would be 90 degrees, so the cosine of that angle would be 0, and AB cosine theta would be 0. But this, like, I don't think in terms of cosines and sines and stuff. I think in terms of this geometric picture. I find it more helpful. Okay, and so now I'm going to introduce unit vectors. Another handy concept. So often vectors are described as being an object with length and direction. And unit vectors are all about the direction. Maybe a better way to say this is these are pure direction. So the word unit here is meant to make you think of the number 1, and so a unit vector is a vector that has length 1. Right? So these are vectors of length 1. And they're denoted by a hat, or I will use a hat to denote them. This symbol, which we call a hat. So instead of putting an arrow over them, I'll put this little wedge, and that's called a hat. So in other words, the vector A, right, so that's just an arbitrary vector, it's equal to its magnitude, right, so its length, and then multiplying something that just points in the direction of A but has length 1. And so we'll call that A hat, right? So in other words, the definition of A hat is the vector A divided by its magnitude. Right, so that's what a unit vector is. And so you can see just from that formula there that the magnitude of the vector A hat is 1. So those are helpful things. And one reason they're helpful is to use in projections. So for example, so notice, if you did this dot product here, A dotted with A hat dotted with the vector B, right? So look back at that expression, those two descriptions we had over here, right? So we said this is, you can either think of it as B times the projection of A onto B, or A times the projection of B onto A. Now, but what is so those A's and B's there are the magnitudes of the vectors. What is the magnitude of this vector here? It's 1, right? So it's, if you think of it as the magnitude of the first thing times the projection of the second onto the first, since the magnitude is 1, this is just the projection of B onto A hat. But that's in the same direction. A hat is in the same direction as A. So let's just write it this way. Right? So A hat dotted with B is the projection of the vector B onto the vector A. So unit vectors are handy in this way because if you dot them onto other vectors, they just give you the part of the vector that points in the direction of the one that you dotted it with. Okay, now we're going to introduce eigenvectors and eigenvalues. So in a proper course on linear algebra, you would spend time on each of these things. The word eigen is a German word. It means own, like my own shoes, or meine Eigenschuhe, something like that. I don't know. My German is pretty bad. But so eigen means own, and eigenvector means own vector, and eigenvalue means own value. And so these are things that are associated with matrices. So let's say you have a matrix M, an n by n matrix, so it's square. Right? It will transform n vectors. Right? That is to say, so let's suppose that these two axes sort of abstractly represent an n-dimensional space. It's really just two here, but it could be anything. Then if you had some vector here that we'll call v, right? If you multiplied v by m, I guess I'll use a different color here. Should I use green? Hope you can see it on this paper. Yeah. Then some other direction and other length, this is m times the vector v, right? So the matrix M has somehow transformed it. M doesn't have to be square. You can transform a vector by bringing it, say, out of its, or into higher dimensions or down to lower dimensions. But having it square makes it sort of easier for me to think of. So this is again meant to be like an x-axis and a y-axis. So this is just a two-dimensional case I've drawn here. And so for us, what we mean by transform here it means stretch and possibly rotate. So it's either, it can do both. So let's say and or rotate. Right? So that's what a matrix does to a vector. It sort of moves it or makes it into some new vector when you multiply it. And so an eigenvector and an eigenvalue, these are things that are associated with matrices, and they are vectors. They're special. They respond to multiplication by the matrix in a special way, right? And so I'm just going to write out what that way is here. So if that matrix looks as follows, if you have m times a vector u, and the result is actually just a constant that I'll call lambda times the vector u, where lambda is a constant. Then the vector u is what we call an eigenvector of the matrix M, and it has corresponding eigenvalue lambda. Right, so let's see if we can write that out. So we'll just say u is eigenvector of M, and lambda is the associate or corresponding eigenvalue. And it's important to see here there's some sort of like degeneracies here, in the sense that if a vector u is an eigenvector of the matrix M, then any other vector that is just like a scalar multiple of it, so like a longer or shorter version of it, is also an eigenvector of M. So the u's are not really unique, but their unit vectors would be unique, because those are the vectors in the same direction as them, but that have length 1, right? So that's important to understand. Oh, also I should say, so this is important enough. You should probably maybe put like a box around it. This is the definition, roughly, where M is a matrix, right? Notice, or an important comment, lambda, it can be 0, or maybe worse, it can be a complex number. And that means it's got a piece that is multiplying the square root of -1. So that's the imaginary number, square root of -1. So that if that happens in a data analysis context, that's usually trouble. In fact, either one of those is usually kind of trouble. Certainly the complex number usually makes trouble in a data analysis context. Okay, so like I was saying, the vectors u are not necessarily unique because any scaling of them will also be an eigenvector of m. It'll have the same eigenvalue. The eigenvalue is pretty unique. But the unit vectors, unit eigenvectors, sometimes called normalized eigenvectors, are unique up to a sign. Right? And so what I mean by that is if you have a vector u that obeys this definition here, and then you make a unit vector version of it, then that vector u hat is unique up to a sign. Right? Now, I'm going to have to make some claims here that, again, you might be familiar with, you might have already proved in your life, or you haven't, in which case we won't be proving them here, but I'm just going to make a claim that there are, so here's the claim. There are at most n different linearly independent unit eigenvectors. Linearly independent, meaning not scaled versions of each other, unit eigenvectors. And we'll name them u hat I with non-zero eigenvalues. Lambda I for a matrix M that's n by n. Right, so if you have a square matrix M and it has dimensions n by n, then there's at most n different non-zero eigenvalues with n unit eigenvectors that are linearly independent from each other. And this number that you actually get, so there's at most n of them, the number that you get is called the rank. Right, so we say the rank of a matrix is equal to the number of linearly independent rows and that's also equal to the number of non-zero lambda i's. Right? That's called the rank of a matrix. Okay, now I'm going to finish today with a series of claims that are relatively important. We'll sort of show a little bit of things about them, but let's just lay them out here. So these are some claims. Right? So here they are. The first claim is that the determinant of a matrix M, so that's written in two different ways. You either write it with vertical bars around M, or you write det of M. That's kind of an older fashioned more old-fashioned version before people had access to all kinds of special symbols. This is actually equal to, and again, this is just a claim, of the product over all I of the eigenvalues, right? So that's a special result. So this gives you a way to compute the determinant, whereas before I gave you a relatively elaborate thing that worked in terms of like reducing the dimensions down to 2 by 2 matrices, and then you could do 2 by 2 determinants. It turns out that the determinant can also be computed as just the product of a bunch of eigenvalues. So you can see right away, if there's a zero eigenvalue, if there's an eigenvalue which is 0, you're going to get a 0 determinant, which means that there's no inverse for the matrix. Another claim is that something that we call the trace of M, which I'll define, that's equal to the sum of all of M's diagonal elements. Like that. This is equal to the sum of all the eigenvalues of the matrix M. That's a cool result. Another important and useful result that we'll make use of, if a matrix M is symmetric, and you should pause the video again to ask yourself, do you know what that means? Because we introduced it last lecture. And I'll just tell you what it means is that a symmetric matrix means that the matrix is equal to its transpose. And so let's say you have a matrix M that's symmetric, and its eigenvectors are called u hat I, right? So the index I is for whichever ordering you do. It's one of the eigenvectors, so it's 1, 2, 3, and so on up to n. The different eigenvectors associated with the matrix M, the unit eigenvectors, I should say. Then for I not equal to j, so if you look at two different eigenvectors, u hat I dotted with u hat j is 0. In other words, u hat I is perpendicular to u hat j. So the eigenvectors of a symmetric matrix are all perpendicular to each other. That's useful to know. That's an important result. Another really important result, these are things that we'll make use of as we go, is that for a symmetric matrix M, or symmetric matrices M, well, that's one matrix. These guys, a symmetric matrix M is what we call diagonalizable. It's a long word, diagonalizable. What it means is that you can express the matrix in the following way. It means that you can write M as the product of three different matrices. A matrix that I'll call X times the matrix that I'll call D, and then times the inverse of the matrix X. And these matrices will look like this. So the matrix X will be made out of the eigenvalues of M as its columns. So we'll say u hat 1, u hat 2, and then up to the nth one, like that. And its inverse, kind of miraculously, is actually just equal to its transpose. Hang on. This is definitely not the normal case, but the inverse of this matrix is its transpose. So in other words, it looks like this. I better put that parentheses after. it's got u hat 1 transpose as its first row, and then u hat 2, let's get that to look correct, transpose as its second row, and then so on down to its last row, un hat transpose, right? So you're supposed to see this as like, these are columns, right? So this is a column, this is a column, this is a column, and so on. This is a row, this is a row, this is a row, right? So that's how x and x inverse look, and D is equal to a diagonal matrix, diagonal, whose elements are like lambda 1, lambda 2, and up to lambda n. Right, and what I mean by that is lambda, these guys are on the diagonal of the matrix down to lambda n, and there's zeros everywhere else in that matrix. This is a pretty useful result, and I'll show you why, and then I'll stop today's lecture. So this is useful for the following thing. Let's suppose you have you want to take that matrix M and you want to raise it to a power. What that means, power P. What that means is that you multiply it by itself P times. So M times M dot 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 times M, and there's P of these P times. Right, so P copies of M multiplying against each other. Well, if you put the diagonal form, right, so let's go back over here and look at this. So here's the diagonalized version, or the diagonal form of M. If you put that in there, what you get is P different copies of this, right? X times D times X inverse. So that's one copy of M. X times D times X inverse. That's the second copy of M. And then all the way up to the pth copy. Right? And again, there's P of those parenthesized objects, right? Now, if you look at this and do the matrix multiplication, here you've got X multiplying its inverse, and that gives you the identity matrix. And that's going to happen at the sort of intersection, or at the place where any of these two copies of M meet. And so what we're going to be left with is just one copy of X on the left, and then D to the P, and then one copy of X inverse on the right. And normally it's difficult to multiply a matrix by itself multiple times, but for diagonal matrices it's particularly easy. D to the P is equal to, you just raise the diagonal elements to the pth power. So for a matrix that's diagonalizable, it's really easy to compute, to raise it to some power. And that's useful because it's going to happen that we have to raise matrices to powers, and that's very difficult to do for in general. But for a diagonalizable matrix, it's very pretty. It works out very nicely. Okay, so that does it for this lecture. I hope you learned a few new things, maybe were reminded of some things you used to know before, or saw some different ways of looking at things that you didn't know about before, and that we're starting to establish a good solid baseline for a common set of mathematical tools that we'll use throughout the class. The next lecture, we're going to do a little bit more of mathematical preliminaries, but they're really going to be specific to, we're really starting to get into the tools that are specific to statistical analysis and multivariate analysis in particular. See you then.